I want to give you some introduction, basically so that we have something to talk about in the breaks and later, and hopefully it's inspirational for your projects as well. So I will introduce you to my environment I have at home in Zurich, so you know where that stuff is coming from, and then hopefully make it into two examples, the first and the third one here, that are examples from our recent work. And I guess I will skip the outlook in the end. For those who have been here yesterday, that was basically the longer version of it. But this is the backdrop in front of which the thoughts yesterday were conceived. Good. So about me, I'm a computer scientist by training, not totally traditional into academics. I studied at an applied science university. After that, I thought, research is cool. Maybe I do a PhD. I don't know what that means, but it sounds somehow attractive to develop new stuff. So I worked on voice recognition and multimedia analysis for almost 6 years. After that, I had enough of research. It's so devastating to work on stuff for 6 years that after 6 years works so I wanted to have a job where I get a question in the morning that I have answered in the evening and then go sleep well. Did that for a couple of years, did some in the automotive industry in Germany, and then switched back to academia because actually there's nothing better than the combination of teaching, research, building stuff up strategically. I work quite a lot in building up ecosystems, associations between industry and academia, research labs. Actually started the first data science research lab under that name in continental Europe, now 140 people. And recently the Center for Artificial Intelligence at my university, 3 years ago, 40 people now. My main motivation as a researcher is pattern recognition. I like to do with the computer what humans do with their eyes and their ears mainly, and maybe from there go a step further into how can we make sense of what we have perceived. I do that with deep learning. It's a great tool for it. There are other tools as well, but my group is studying pattern recognition with deep learning. So about the research center that I'm directing. We are 3 years old, roughly 40 on staff currently, potentially approaching 60 in about 4 years. That are the projections. And doing research and method focused on machine learning in all kind of industry, almost. We haven't worked a lot on finance. We haven't worked a lot on defense. But in almost all other areas, from really hardcore producing industry to medical, aerospace, and so on. And you see here the 5 areas we are working on and the 7 research groups we are currently having. The idea is, so this is my group here, the Machine Perception and Cognition group, which is mainly working on this research theme of the center, computer vision, perception, cognition, a little bit in autonomous learning systems. So I'm really fascinated of deploying algorithms on robots. Haven't done that so much, but increasingly. And I'm quite interested in how to make these systems trustworthy, which can mean different things. It starts with the methods being robust in an environment, so they actually work, and spill over into being interpretable, and even societal aspects of it. We talked about that yesterday more. So my concrete research group is this, the Machine Perception and Cognition group, with my lovely staff. Ahmed, next to me on the slide, is currently leading my group while I have the great opportunity to be abroad and just give cool talks. Couple of PhD students, and we have been working on a number of very, very different things. If I look back over the last 10 years, there tend to stand out a couple of pillars on what we have been working on. One is definitely medical applications, mainly medical images, improving computer tomography scans, doing object segmentation in medical images and so forth. Another pillar has been document recognition, working on documents that are intended to be read by us, by humans. But in the name of automation, it would be great if the computer would understand these documents as well, so it can help in certain tasks. And we have been working on music recognition, for example, sheet music recognition. Currently, we're working on engineering sketches, things like that. How can you make sense of it? And finally, industrial applications. Industrial understood really in the sense of producing industry, machines, metal, oil, stuff like this. A lot of work has been in that area. And the fundamental challenges tackled by means of that use cases typically went in the direction of, okay, how to make the stuff robust for the real world, because you probably know there's a difference in ouncing out the last promille on ImageNet classification and doing something that somehow works in the real world, even if today, I don't know, the sun is not shining or whatever. Or the camera has changed and stuff like that. So in order to make it robust, we had to work on sample efficiency and label efficiency because, well, industrial partners are not so much inclined to get you 10 million labeled examples of whatever they do. If we ask the medical doctors if they can label 10,000 computed tomography volumes pixel by pixel, they will like show you gestures like that. So they asked you, okay, what can you do with 5 labeled volumes? And actually, turns out one of our recent publications showed what we can actually do with 5 or 10 images, plus a bunch of unlabeled work. So a lot has been in sample efficiency, label efficiency, in transfer learning and domain adaptation for the same reasons. How can we leverage data we find on the web, build a base model of it, and then adapt it quickly to the case at hand. Trustworthiness plays a role. Our curiosity somehow factors in as well. And that's typically a good mixture for happy industrial partners and great scientific publications. That's always what we try to achieve in parallel, neither only the one side or the other. A recent highlight, just to show how we work. 2 years ago, I was on a similar trip like this one, and I met a colleague. She was a professor of biophotonics. I had no clue what that is, but over a coffee, we got to chat, and she said, I have a new method that can actually help diagnose cancer, a certain form of cancer, much more quickly than typical. So you don't have to send the patients home anxious, sleeping a night or two over it, thinking they might die or not, you never know, only to come back later and hear the result. But with that method, you can give the result immediately after 20 minutes. And she said, the only drawback is there's only one person in the world, my 5-year postdoc, who is trained enough to do the image segmentation necessary. I said, well, I have no clue what you're talking about, but I'm from AI. We did a lot of object segmentation in the past. I think we have methods to do that. If you have a person who can do it manually, we should be able to do it. Let's try to find 2 bachelor students. They typically work in pairs at our university on their bachelor thesis, to try that out. And we just took a off-the-shelf method, the UNet, applied it to that problem. Actually, it worked. We now have a publication together in Nature Scientific Reports that basically shows this can very, very easily be done in 5 seconds with a standard UNet. The postdoc now can do a serious job and not have to do all the manual segmentations all the time. And a colleague from Harvard came across Harvard Medical School and told us, like, do you know that your method now will change the practice of how cancer is diagnosed in doctors' practices worldwide? Which is super cool for a bachelor thesis of 2 guys who just 3 years ago did an apprenticeship in software engineering and now won numerous awards for their thesis and somehow changed the world a tiny little bit. So this is the kind of work we really like to do. Sometimes it has more ingenuity from AI. Here it was just taking what works and applying it to a new domain where it was unknown. Really cool stuff. With this, let's look into our examples. First one actually is motivated by the work we did in optical music recognition. So just to give you a background of the project, at some point a startup company approached us and said, we have the vision that musicians could play from iPads, giant iPads, instead of their manual sheets. Why? Because the wind may blow it from the music stand, or you forget it at home, or you need convenience functions like the conductor in an orchestra says we play from measure 760, and that means page 1 for the triangle and page 50 for the first violin. So the conductor can just click on the iPad and every page flips to the right page. Things like that. They're only possible if you have a machine-readable music sheet, and that is something different from having a PDF that you can display. which is not machine readable in itself. So we worked on optical music recognition to solve the chicken and egg problem of that music publishers are not so inclined to give out their music in music XML. But they would be very happy if there's an infrastructure around it to do it. So we needed something to start it off. And we worked on OMR very successfully. Basically, we were the first publications on using deep learning for OMR, which worked like a charm, bringing down the error rates by 1 order of magnitude. After our first publications, basically the whole field changed to now it's only done with deep learning. So that was really successful. We liked it a lot. We found out a couple of issues when approaching object recognition for these tiny objects with convolutional architectures, which we used at that time. And one of these challenges was that some of these objects here, these how do you call it, slurs, ties, they can appear at an angle. They're not always flat. They can be angled, which is difficult to detect for a convolutional network. For them, it's basically each angle is a different object. So we had bad recognition rates on specifically these objects. And my PhD student started to look into that, thought, there might be a more fundamental problem. Can we tackle that? And he looked into the literature, and what did he find out? He found out that regardless of if you have a convolutional architecture or an image transformer, basically, the recognition accuracy is only good for the canonical 0 degrees rotation, the canonical representation of the object, like when it's upright, so to say. And if you deviate from that canonical 0 degree angle, the recognition accuracy drops dramatically, almost to 50%, depending on the angle, as you see on these polar plots. So that's a problem, and of course, there are solutions in the literature as well. Rotation equivariant architectures or data augmentation, both we found out are more a theoretical solution. They work, you can also show experimentally that they work, but they basically blow up the number of parameters in the model, the number of data you need or you artificially create with rotation. So these models tend to become much bigger, which makes training much more difficult and every inference step computational more costly. So these are not solutions that a real-world industrial partner would like to implement. These are solutions you can basically publish at NeurIPS, but nobody will ever use them. So, which could be nice as well, but we wanted something that is useful. So we thought, is there a better way than blowing up the number of parameters for our model and basically detect every object at every angle in itself? And Lucas, my PhD student, found work from the 1970s, from psychology, neuroscience, that basically had that interesting finding. We humans, tend to take longer to recognize an object that appears at an angle, and the time we take longer to recognize it is in proportion to the angle, to the difference of angle to upright. So basically, if something is on its head, we take twice as long to recognize it than when it's upright. And these researchers concluded that what humans do is they do not recognize objects at every possible angle. They do something like a mental rotation. They rotate the image a little bit, try to recognize, doesn't work, rotate, until it's upright and they can recognize it. So there seems to be an iterative process in the brain. And we thought, oh, well, that's super interesting. That can be simulated by machine learning as well. So he came up with an artificial mental rotation module that basically does exactly this. And he implemented it as a snap-on module. You see it here in blue, that can be snapped onto any convolutional or transformer architecture. So what is it doing? It's taking out that are the arrows that go down here. The features computed by, let's say this is the gray one, a standard computer vision backbone. Trained on ImageNet, pre-trained, works very well, right? You can just leverage everything you get from the web. And we take out the features at every layer. and train a second very, very lightweight, small scale architecture that in the end classifies the angle of the object shown. And once the angle is detected, we put it through a small script that rotates by minus the angle, and then shows the image a second time, and this time we classify the image itself. So we double the inference time because we have to do 2 passes, but it's fixed, just double, not number time so and so much. And the training is very, very lightweight for this mental rotation module, and it works really, really well. You see here again the polar plots. The yellow is the standard baseline. Nothing is done for rotation. It only works for 0 degrees. Green is if we do data augmentation, the standard data augmentation. And blue is our mental rotation module, which outperforms the data augmentation consistently and works as well as a baseline for any angle. And the coolest thing is it automatically and without any further ado transfers to segmentation. So it's not classification dependent. It also makes semantic segmentation better. So it seems to be something that works in principle. So what we can basically say is that this solves the 2D in-plane rotation problem for computer vision sufficiently. Nice thing, or not so nice thing for the PhD students, we tried to publish this at all the major conferences. Finally, they had nothing more to complain. It got only accepts at ICML, and it was rejected for, well, it's boring, it's such a simple idea. Yeah, exactly. Well, maybe we should take it as an honor. Like, it's a simple idea, it works, doesn't need whatever. So for us, it was a really cool project because it was motivated by a real-world problem. The idea came out of a different discipline, inspired by how we humans work, and the result shows that it really fundamentally works well. Really, really cool thing. Second idea of second project, and from this I want to, if time permits, take off into some future stuff that currently is interesting for us, and maybe there are ways of collaborating on this. And if there is anything that is not yet fully worked out, that is because what I show you now is completely not yet published, finally, and work in progress, and some things might be still change with results coming in and so on. So, but we can discuss that later. So again, what's the setup here? We work with an industrial partner. The industrial partner produces pressure sensors. And one of the use cases where you can actually use pressure sensors is to monitor plastic injection molding processes. So what is plastic injection molding? It is basically the industrial process, to produce things like this. Maybe not the bottle, it's produced differently, but the cap. Or the cover of your iPhone, or these kind of things. So plastic parts are typically produced by plastic injection molding, which means you have plastic material that is melted and with pressure injected into a form, the tool, and then it is cooled off, the form opens, and the final part falls out. In the tool, we have the pressure sensor that basically measures a curve like this. We call it the elephant curve. You see it, right? This is a tail, here is a head. That's an elephant, of course. This is the time series over how the tool is filled, the pressure is held, and the pressure is released, and the thing opens. And out of this pressure curve, people found out you can determine if the part is, for example, not fully filled. This is when the pressure was too low, or if it is burned at some places and has dark spots, which is also not good quality. This is when the pressure was too high. So you can actually use that for quality control. But at the moment, it works like this. Humans have to go and define these squares, which in their lingo is called, what do they call it? An evaluation object. And it's placed manually so that a curve has to pass through the green parts and must not pass any of the red parts. This is done manually by engineers who have lots of training and experience in it. And you have to adjust it for every aspect of the environment, like humidity, temperature, the bag of plastic material you use, the form, and so on. And if any of these parameter changes, you have to adjust these evaluation objects. Challenge was build a machine learning model that can do that. And we had experiments that showed, yes, it works for any certain situation. But then if over noon the sun comes up and shines through the window on the machine and it heats up by ½ degree, model doesn't work anymore. Curve looks different. If your bag with material is empty and you open another bag with different humidity of the plastic material, curve looks different. So the problem is, how can you build a model that understands these elephant curves and then transfer it with very, very few scrap parts to any given environmental situation? New tool, new customer, new machine, and so on. So we have been told by experts in plastic injection molding, so materials engineers and so on, that this is impossible. We should just not try and go home. Because they did PhD theses on that for 50 years and it just doesn't work. And we said, well, we have a different methodology here, let us try. And what you see here is a very simple model, basically our second idea. And after 1 year, this part of the problem was solved, the anomaly detection. So let me explain to you how it works. And for the moment, let's center on this middle image. That's the architecture that we use. So what we see here is an encoder-decoder architecture, specifically a variational autoencoder that encode here. That's a vector of the whole time series of the elephant curve. So you can imagine that there are 1,000 samples. So this is a 1,000-dimensional vector. And we encode, decode to the same 1,000 dimensions, and we have a reconstruction loss here. So this should equal that, or the other way around. This xp hat shall equal xp. And the internal representation that we learn is basically the mean and the variance of a distribution of just a 2-dimensional representation. Why 2 dimensions? Well, because it's simple, you can visualize it. And we thought we start with this and then get more complex, but we didn't need to get more complex. So it was arbitrary and chosen so it's easy to visualize. And it worked, so we had no reason to enlarge the representation. So that's only one part, the upper part of the architecture. The lower part, basically here, you see with the arrow to ZM, is a regression model that tries to regress from the learned representation to the 3 main machine parameters that influence the shape of the curve, which is the holding pressure, some temperature thing, and a third one. And basically, we have 2 tasks. First is to detect anomalies. Second is, if we detect anomaly, to predict which of the 3 main parameters we need to change in which direction to recover the good process. On that second problem, we are still working with some progress, but not final victory. First problem is solved. So anomaly detection works very well. How does it work? Well, we have 3 phases. This is now the right pane of the of the slide. We have an offline training where we use hundreds of thousands of curves from different processes, different plastic materials, different customers, all kind of variety in the process and different machines and so on, and use all these unlabeled data to train the variational autoencoder architecture so that it in principle understands how these curves look like, without any labels yet if something was good or bad. Then for any particular situation, so a particular bag of material, a particular product on a particular day at a particular machine at a customer site, we use something like maybe 30 scrap parts, which is commercially okay for the creators of such products. 30 parts to calibrate what is an anomaly and what is normal. So basically, from the distribution we learn here, the mean and the variance, we determine how far away should the threshold be for stuff that is still good. We get that quite well with something like 10 to 30 parts, and then we can online monitor the curves that come in and see if any point is within or outside the circle. So that solves the anomaly detection part. We showed that the engineers were wrong. We were very happy that that worked. And you can bet my PhD student who's working on that was very happy that it worked. Published that this year at the Swiss Data Science Conference, which is a cool venue to publish stuff. Its deadline's coming up in February. Exactly. What we are now working on is how to do the prediction of what should change. in order, when something is wrong, which parameter needs to be changed in order to recover the good process. And the basic architecture you see here on the left is still the same. We have the variation autoencoder, but we changed the input and output. You see now with the red and green here that we input two curves. So we embed a pair of curves. And we're not learning the parameters directly. You see here a delta in front of the x hat m. We are trying to predict the difference in parameters that explain the difference in the two curves. So the curves come from the same environment, machine, customer, material, blah, 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 all the stuff. And the difference is just different settings in the machine parameters. We get them from controlled experiments where we did systematic change of all the parameters. And if we train the system like that, again, here you see it on the right hand, we have the offline training, then we have fine tuning for the specific situation with something like 30 parts. And now you see also here the prediction of the machine parameters. It works quite well, but what we find out is from the 3 parameters, we only get disentangled any 2. So there's always one that is entangled with one or the other. So basically, the model gets it right, which parameter needs to be changed, but we have no clue to know which one it is. So the stuff is still entangled, and we are working on this. The current idea is, who knows the ZHAW architecture that Jan LeCun was presenting in his Towards Autonomous Machine Intelligence paper 2 years ago? So that was a very interesting paper, not much research, a lot of opinion, but showing some direction of somebody who has seen a lot in machine learning, right? And he was presenting this joint embedding predictive architecture that embeds 2 things and tries to model it not on the level of the inputs, all the differences, but to explain it on the level of the representation. And currently what we are doing is morphing this architecture into something that looks more like ZHAW. So here you actually see Jan and the figure from that famous opinion paper and the ZHAW architecture. And that now, let me use it as a springboard to stuff that is currently on my mind research-wise. So I spent the last 3 months, plus minus, at the Institute of Neuroinformatics at the University of Zurich. They do very interesting stuff. They analyze brains of monkeys and of mice, and try with experiments and sensing, try to find out principles, how the brain works, in order to use them to improve machine learning. And also for other reasons, but that is what is interesting to me. My host there, Professor Greve, has a group that has actually, neuroscientists working with mice and machine learners working with deep learning models. And one thing we are working on is architectures that could become proper world models. So what do I mean by world models? Models, neural network models that understand, let me draw these things into the air, it's always tricky with the terms, that understand enough of the world in a way that is common sense-like, that you can use them actually to plan actions. And yes, I understand there are currently ways how you can do that, but let me tell you briefly the problem with the current methods. Currently, methods are trained, for example, transformers, in an autoregressive way during pre-training to just predict, for example, the next token. So what you get out is a representation that is perfect for exactly the task it has been trained on. It's very, very good to predict the next token. That means that the internal representation at the embedding layer in these methods is structured in a way that is exactly good for that. We shouldn't expect that the representation is very helpful in interpreting what's going on, why the result comes out, how we can steer it to give different results. It hasn't been trained for that. We shouldn't expect this. Now, go a step back and think, how are we humans working? Have we ever been trained to just spit out the next token? Very rarely, if at any point, right? What we do from early infancy on is we are goal-driven. We have some goal in mind. It could be I'm lying on the ground here and I want to crawl over there, or I want to roll over to the other side, or I just want to feed. So we have a goal in mind, and everything we do is goal-driven. So hypothetical, assumably, our representations of the world, our internal world model is structured in a way that allows the derivation of actions that bring me to the goal, which also means that these representations in our brain are presumably more interpretable towards what does lead me to the goal. Our model of the world is more a cause and effect model, because this is exactly what we need to do. Like, I want that effect, what do I need to do to cause it? When we just train for predicting the next token, or classification, or label, or whatever, we don't train a cause and effect model. And I'm talking loosely about cause and effect. I'm not talking about causal AI at the moment. Just about the structuring of the latent space. So, very brief idea. Biological learning is goal-driven, leading to actionable representation from which I can derive actions and enroll them long-term. We have experiments currently that show when we learn models a little bit more in that direction, we can unroll a plan of actions for a example robot navigation task, thousands of steps, and be millimeter precise with our navigation at the very end, just by thinking forward what you need to do, because the model is structured in a goal-driven way. Current machine learning is prediction-driven, gives us something else, gives us perfect compression, which is a cool principle. You maybe know the paper by Jürgen Schmidhuber, Driven by Compression Progress, which is a great paper. You exactly get what you trained for. You don't get something interpretable. So how can we go in that direction? Brief idea, and I finish. If we want to go towards world models, think about what we see as humans. We have an environment around us, for example, with the sun and trees and a bird. We somehow sense it with our sensors, ears and eyes. From this, we get observations, which is already not the same thing as the real world, right? It's some sort of a representation. And this now we bring into representation in our internal world model. These are our feature vectors that are hopefully, in the end, creating a mental picture, still speaking about the brain, that is somehow in correspondence with the reality that we cannot see. We only see the observations, and from this we only get our representations. But what we would hope that is that our internal world model allows for predicting the dynamics that is going on externally in the real world. If we have this, we have a world model that is useful, actionable, to do something in the world. We can plan with this. So how does this translate into more formal machine learning terms? We have some environment vectors S, we have our observations O, we have the representations in our model, the brain or the neural network, Z. These are statistical descriptions of what is going on. Now, it is not enough to just model the single observations, which is what typically in deep learning we are doing when we are predicting labels. What we would actually like to do is, I mean, in the real world, we have something like a state transition matrix of what can happen after what. Like when I'm here and I'm doing a step, I cannot end up outside of the door. That's a state transition that doesn't exist. But one exists that brings me here or here and so on. So what we want is something like a homomorphism, maybe not in the most rigid way, between possible state transitions in our internal model, in our world model, that are homomorphous to the possible state transition in the real world. If we have that, we have a model useful for planning. Now, the problem is if we want to learn this, we have no actually access to the states of the real world. Remember, we just have the observations. Now, but what we can do in controlled experiments during training, we can make the agent do certain things, observe cause and effect, and try to model this. And that has been published by Benny's group at Institute of Neuroinformatics under the term homomorphism autoencoder. That's basically a model that, with an autoencoder, encodes observations into some embedding space Z and the possible actions in the real world, which in that simple example was just move the object left, right, up, down. They're embedded into exactly the same dimension in a way that if you add an observation vector to an action vector, you get a new vector that you can interpret as an observation vector. And if you decode it back, you should get how the observation looks like when the action is applied to the input. If you can do this, That would be great. And actually, it works. Does it move? No. Okay. That could have been animated. Anyway, it turns out that just this way of training it, which is a little different than just predicting the next token, leads to an internal representation that is structured in a way, the learned space is structured in a way that allows these kind of long-term predictions. And what we are currently doing is working towards adding a couple of other things, making it a little bit more realistic than moving hearts on a square, and trying to use that for the use case of robot navigation. Okay, I think I stop here. But these are a couple of ideas how you can start with an industry collaboration, see certain limitations, get inspiration from other fields, and hopefully revolutionize AI in the end. Thank you.